All right, hello everyone. Today we're going to be doing a Lab 2 help session. So I actually just did this help session in person, but unfortunately the mic wasn't working, so there wasn't audio on the recording. So I'm going to take the next 30 minutes and kind of recap what we talked to. I'll hit all the key points, and then I'll also try to summarize some of the popular questions the students were asking so that everyone gets that same kind of insight. So let's see. We're going to go ahead and start with a lab one review, talk about some common mistakes that me and some other Pi saw through the lab one review. We're going to start with a MUX truth table, 2 and 4 inputs. We're going to do some Quartus simulations, some pin assignments, and programming the DE10 Lite. And then we're also going to do the decoder truth table and the kind of skills you'll need for that one as well. So to start off with our lab one review, everyone better either remind themselves or make sure they understand the switch and LEDs on breadboards, because this is not going away. We're going to use this for a lot of subsequent labs, and these errors tend to propagate. So we want to catch them as early as possible. So for here, this is an LED segment I drew. If you have an active high signal, let's say A active high, you're going to want to wire this up to the anode, or the side you'll see with writing. And then the adjacent side is going to be wired to ground. This side is going to be called the cathode, or the grounded side. Likewise, if you have an active low signal, in this case B active low, you're going to put that into the cathode and connect the anode to 3.3 volts. So this is because LEDs are polar components and need to be wired exactly like this so that you get the intended output. And then if we flip over here to the circuit diagram, or the switch diagram, a lot of students ask, why is an A active low in the high, like up, pushed up the true position, and why is B active high pushed down in the true position? Because this is basically saying when the switch is flipped up, the ground connection is active, so the switch is closed. So for this one, when the switch is closed, this signal will get pulled down to ground, and 0 volts for our active low signals is in the true position. And consequently, when this is down low, it means the switch is not closed, so there's no connection to ground, and the output will be 3.3 volts, which is true for our active high signals. So that's a quick clarification for anyone a little confused. Secondly, demo videos. It is required for every lab, lab 0 through lab 7, to have a demo video at the very bottom of the lab doc. When it talks about the in-lab portion, that will be your demo video. You'll demo the fact that your breadboard is working, you've completed all the parts of the lab, and this will expedite the process for you and your Pi when you demo. So demo video is required for every lab, preferably with a clickable link. It'll make it so much easier on your Pi. Another issue is if you go to simulate and there's no nodes when you click list, it's probably because you haven't compiled your BDF yet. So the simulation can't see any of your inputs and outputs. Contrarily, if you click the list in a simulation and a whole bunch of nodes pop up, that means you forgot to unclick the top level design. And the way to fix this is if you go to the Files tab, you'll see it's like DE10 Lite golden top. Delete that file, and then click your BDF to be your top level entity, and that'll solve the problem. Again, bring entire lab kit and pre-built breadboard to your lab. Don't disassemble your pre-lab before you get to lab, because you will have to demo it. And lastly, uncheck top level entity. This is kind of what I was always talking about. So let's go ahead and dive into our lab 2 concepts. So first, we're going to start with a 2-input MUX. So the idea with this is you have 2 inputs, D1 and D0. These are what we call our data lines. And you also have the third input, which is your select line. So depending on the value of this line, depends on which one, either D1 or D0, gets fed to the output. So you can see down here, I have a truth table for this 2-input MUX. So you can see when S is 0, data 0 line is selected, and this will be directly connected to the output. Likewise, if S is 1, D1 will be selected, and these values will be on the output. So normally, when you have 3 inputs, you have 2 to the third, or 8 rows. And here we condensed it into just 4 rows. This is because we use something called wildcards, or you might see this as an asterisk as well. It basically means that this row encompasses the data for 0, 0, 0, as well as 0, 1, 0. And the reason we can do this is because since it connects, like let's say D0 to the output, no matter the value of D1, this output will still be 0 because it's selecting the D0 line. So if we go over here, we can think of this as opening up our block diagram, and you'll see something like this inside. So we have our S, and then this is essentially our D0 and our D1. So when this S is 0, 1, it goes through, propagates, and you'll see this when you design your circuit. Lastly, this is going to be the KMAT format. So if you want to practice your KMAP skills and see how this works out, I basically took the outputs from here, fed it into a KMAP. So this is S01 and D1 and 0 right here. And you can see in blue, I did the sum of products. So I circled these two terms. This is the biggest circle I can make. S stays the same at 0, so we get not S. Here we can say D1 changes, so we can remove that. And then D0 is 1, so we can AND D0. And then we'll OR this with our second circle. You can see S stays the same. D0 will change, and D1 will stay the same. So this is how we get S, D1. Same process here for our product of sums. And now I have a quick Quartus demo. So if I open up Quartus here, should still be sharing this screen. So right here, I have this sum of products of the MUX. So this is basically what I was showing you on the previous slide. I've already compiled it, so we'll go ahead and look at a simulation. So I'll go here to Files, open up my waveform, and then we will go ahead. Let me make sure the settings are correct for this before it throws an error. And then we will run this. So this one shouldn't take too long to run. All right, so there we go. So here we look at a snapshot right here. You can see that from S is being 0 or selecting D0, it mimics the output, will mimic D0. When S is true, it'll mimic D1 straight there, just like that. So if you notice, when you have a 2-input MUX, I went through all 8 of the combinations, which is not necessarily wrong, but you can see when we get to more complex MSI components, like a 4-input MUX, now you have 4 inputs, 2 select lines, 2 to the 6th, 64 combinations. It's not efficient to show all 64 combinations. So when we get there, I'll show you maybe a more efficient way to prove to yourself that this works. So again, this is sum of products. So you can see matches D1. And now I also have a BDF here called product of sums. I'm going to right click this, set this as the top level entity, and then compile this. So now when I do my compilation, it'll look into my MUX to input product of sums. And again, I click this right compile because we're just simulating for now. I'll open this waveform back up, go into simulation settings, and you can see right now it's still looking at the SOP, our stored defaults, and now we're looking at the POS, which is what we want. I'll save this and run the functional simulation. And you can see that it essentially does the same thing. When S is 0, it mimics D0. When S is 1, it mimics D1. So this is basically as close as a proof I can get for now that the product of sums and the sum of products are equivalent. So if that was something you were interested in looking at, there's a quick example for you. So now I'll go back to the PowerPoint here, and we will move on to 4-input MUX. So it's essentially the same process, except for now we have 2 select lines. So we can select a line 0, line 1, line 2, or line 3, and it basically reflected. So in your lab, you'll actually have bubbles on some of the inputs and outputs. To remember, this does not change your truth table, but it will change your voltage table depending on your activation levels for your gates. So yes, and then another thing, this is a picture I got from the internet. You notice they physically connect all the wires. What we want to do in this class is, for example, if we have this A, we'll call the end of this wire not A, and then we can virtually connect the node using these labels. So this gets rid of all this jumbly wire mess in the middle and allows us to read our designs much more clearly. So I also have a Quartus demo for this one. So we'll go in here. We'll set our 4-input SOP to top level and we'll compile it. So for simulations, we're using this right one. And then if we want to do a full compile and push it to our D10 light, we will have to use this left one. So after this compiles, pretty quick, we'll open up this second waveform. And you can see how long the simulation is. 0, 0, 0, 1. Very tricky. So let's go ahead, restore defaults and try to run this. All right, so there we go. So it's a lot more evident what line is being selected. So here I grouped the select lines, so 0, 0, and it matches D0, 0, 1, and it matches D1, 1, 0, matches select line 2, 1, 1, matches select line 3. So all of these things would be meaningful to have in your annotation. So maybe I'll highlight this and I'll highlight this. And then when the select lines change, maybe I'll indicate that going down and highlight this and highlight this. And then give some sort of explanation showing that when the select lines change, no matter what's on the other lines, only the line being selected is what's being passed to the output. So of course, this is very complicated and a lot to look at. And you can simplify this down much quicker, but you'll see how to do that in your lab when you do that. So that's the 4-input MUX. We go back to the PowerPoint here. We will move on. So yes, in your pre-lab, the activation levels will change. Use mixed logic in your gates to account for these changes. All right, so we'll move on to the decoder. So this is the block diagram for the decoder. And basically, the idea is we label this A, B, and this corresponds to the output of the decoder. So instead of previously, if you want to represent these 4 bits, you need 4 LEDs. And if you'd want to express a binary 4, you look and X2 is on, and then you have to do the binary math in your head. That gets quite tricky. So what we can do is we can feed the output of our circuit into this decoder, and it'll convert it to A through G, which will output on our 7-segment display. So we can look at a nice number like 7 rather than like 0, 1, 1, 1, right? That gets a little tricky, especially when you have larger outputs. So yeah, we can see our outputs easier. Another thing to note is that all the LEDs on your D10 light are active low. So that means if you want to turn it on, you need to send a low voltage to that pin. So for the decoder, you'll make a truth table kind of like this. So basically on this left-hand column, I'm saying this is the digit we want to output on our hex to 7 display. So if you look at 0 and then reference this image, everything will be on except for G, and then maybe H if you decide to do that. So then in our table, you can see everything is true except for G. Likewise, if display a 1 here, and then this is the binary equivalent, B and C will be on, and you can see that reflected in the table. So Dr. Schwartz does give you a lot of these. I do believe for this lab, you will have to do the sum of products and product of sums for both A and B. So these two right here, as well as the sum of products for C. So these will actually end up being probably quite long equations because if we have A, it's like E, F, A, B, C, and G to output an A, which means there's a lot of combinations that'll do this. And then, of course, you'll use the mixed logic voltage table conversion like you did in lab 1. And I have a video on that if you get confused. So lastly, the thing we'll cover is a MUX implementation. So I have an equation right here um, where one variable kind of shows up each time. And you can notice this B is ANDed together right here in the middle. So it basically says the equation can only be true if B is true. So B can be routed to the enable input. Because if B is ever false, this equation will always be false because anything ANDed with 0 is going to be 0. So what we do is you can think about factoring out this B and we'll save it for an enable and we get left with not E, D, or C. So now we use the idea of selecting inputs or data lines to our advantage. So typically you want to pick the two variables that show up the most common. Otherwise, just choose whatever two you want. In this case, I chose A and C since they all appear once in this equation. So you basically count from 0, 0 to 1, 1 and plug them in to this equation. So for example, A and C is 0. So this first term doesn't have an A and C, so we'll leave it. And if you plug in A here, it's 0 and not 0. So that's 0 and 1. That term will go to 0. It's all knotted right here. So it'll go to 1 right here. And we get left with not E or D. The same thing kind of applies for 1 and 3. And if we look at 2, not E or D stays the same. And if we plug in A here, we get 1 ANDed with not 0. So that's 1 and 1, which is 1. All of that knotted will give us 0. And anything ANDed with 0 is 0. So effectively, we can tie this data line 2 to ground since it'll always be 0. So I guess I have a mouse here, but I'll try to draw the implementation. You'll have your MUX here, and you'll have S1 and S0. So this will go to S1 and 0 active high. And then we're going to make our little enable right here. And we'll tie this, we'll say B and call it active low. And then of course you'll have D1 or up here, I'm sorry, it'll be like, I think maybe it starts at D0, D1, D2, D3. And then of course you have not E or D. So maybe we'll have E. Let's just say E is active high. We feed it into a BOR gate. And then here we say D active low. So there's no mismatch on D, so it'll stay D. There's a mismatch here, so this will be not E, which is what we want. And we'll feed this into D0, D1, and D3, and then D2 will connect to ground. So this is essentially how you would implement something like this, and you'll have Y in your outputs. So something like that for the MUX implementation. So the last thing I'm going to want to talk about is this is a snippet from your pre-lab document. It says demonstrate the following circuits from the pre-lab. So this is what you need to bring to lab and you'll demo to your Pi. And there'll be a similar snippet in all the next labs so you don't get confused. So 2 input MUX made with SSI chips. So this is like discrete components you might see as the little ICs. The 4 input MUX made with DE10 light. And then Hex the 7 segment decoder made with DE10 light. And something I will also go ahead and show you that I forgot to do it when we went to Quartus is if, let's say we go back to this 2 input stop, or actually we'll do this 4 input since you'll have to do this something similar in the lab. And you'll get your inputs from the switches on your breadboard, and then you'll feed it into pins on your DE10 light. It'll essentially do all this calculation for you and then spit out an output. So the way we do this is you'll have to do a full compile, which has already been done. And then you can go to Pin Planner through assignments, Pin Planner. you can see this big, really confusing wire bond board shows up. So we can ignore this for the most part. Um, and if we go to the website, so let's say we go to the website here, go to software docs, and we go to D10 light pins. So this is everything on your GPIO ribbon. So D10 is your dedicated clock pin. So let's say we want two inputs, W10, W9, and our output W8. Going into Quartus, we'll type in these, so like pin W8. So when you wire the input of your switch into this, it's essentially D0, and then we'll output, let's say Y is, what was it, W9? So pin W9. So this is saved. So now we can close this. And in Quartus, you'll do another full compile to solidify this. And then after Quartus has compiled, you'll be able to open your programmer here. You can see this is the soft, which is what we always want to program. I don't have a D10 light connected right now, but you'll program and verify and then click start. You'll see if you have the safe program on your POF of your D10 light, the numbers will go away. This means it's been successfully programmed, and then your function or your circuit will be able to work correctly. So that is pretty much it for this video. I'll go ahead and end it there. If you guys have any questions, go ahead and maybe put in the comments of this video and I'll try to answer them and clear up anything that might be a little confusing. So that is it for now. Thank you, everyone.